The Navy wants to be energy independent, energy resilient, be able to respond after a disaster or a military situation. So renewables just add to your flexibility in terms of power generation in many, many scenarios. Here in Hawaii, we've made a lot of progress integrating solar and wind into our grids, but we're still very reliant on those fuels. In a tsunami situation or a major hurricane strike that closed our ports, we'd be in a world of hurt in terms of energy generation. So that's another motivator to bring more and more renewables. WETS, or the Wave Energy Test Site, is unique. It's the only grid-connected wave energy test site. There's 3 test berths. They're each cabled to shore with power and fiber. So it's the only such site in the United States and one of only a few in the world. It was developed by the Navy with congressional funding for the purpose of testing wave energy converters, prototypes or early stage concepts on their way toward commercialization, where they need to do testing and demonstration in the open ocean to validate their technologies. So we have now supported a number of deployments by working with those developers to help them prepare and plan and then execute. We also get involved in inspections of the devices and the moorings while they're deployed at WETS, just to keep an eye on things and document whatever might go wrong or need to be fixed. We've got 3 wave energy converters, we call them WECs for short, that are kind of on our plates right now. One of them is behind me from Irish company Ocean Energy. There's 2 others, Oscilla Power and Sea Power, Sea Ray. The Sea Power folks have actually completed their deployment and are in the process of recovering their hardware. And then Oscilla Power is here in Hawaii and poised for a short deployment soon. Our group at the university supports NAVFAC, the Naval Facilities Engineering Systems Command, their Engineering and Expeditionary Warfare Center.
Hona is an oscillating water column wave energy converter, and what that design means is it's a platform that floats on the surface, a buoy essentially, a hollow cylinder that uses the ocean waves, and as they pass through, those ocean waves push air up through a cylinder, spinning a turbine to generate power. I think the ultimate purpose of the Hona WEC is to power the blue economy. You know, this is a budding energy industry, and what we're eyeing for this platform is for it to be a stable platform that can generate power for a multitude of open ocean uses or inshore possibly, you know, sensor packages, ocean monitoring, environmental monitoring. What we've been working on is a system that generates dependable power at a low cost and low maintenance cost. The majority of the parts are all 3D printed and easy to design, easy to build, easy to replace.
We're working on multiple scales of this device that can be applicable for different use cases. So a smaller scale could be used for small sensor packages, and a larger scale could be used to power aquaculture and bigger things.
The Navy could choose to use this for, you know, passive sensing off in the open ocean. Its physical design, I think, is really, really great for DoD aspects because it has low visibility. It's a very small surface profile.
I think another key aspect that the Navy would be interested in is the autonomous nature of the device. It generates power on its own and can power the sensor packages, presumably 24/7, wherever it's deployed.
Moving forward, our goal with Hona now is to complete, you know, our lab testing in-house, but ultimately the goal is to start doing ocean testing and putting prototypes out in the water and advancing the model and the PTO as we go forward. It's not just testing the power performance, it's also testing, you know, what sensor packages we can design and put out there. We ultimately want to add AUV docking and drone landing to the surface of the buoy itself.
The FOSSEC is a floating oscillating surge wave energy converter. It's a dual flap type system. With the waves passing through incident, they cause a pitching motion on the flap, and that's how we generate electricity through a direct drive PTO.
We are basically supporting the Navy in achieving very low visible underwater power technology, but what we are bringing to this device is a mooring system which will work in intermediate or deep water. This is something that no one has tried so far, so that's the newness of this technology and how it's useful to the Navy.
We're going to be going into Oregon State University, where we'll be doing testing in a wave flume. So this will allow us to collect data. We'll use that data and use it to validate our models, which again, we're talking about as a design tool, feeding this to the Navy as a design tool that they can later reference when they want to analyze whatever specific locations where they want to deploy this.
The OWC breakwater is an oscillating water column integrated into a slotted barrier breakwater. It's going to be used for the Navy for rapid harbor development. Here's a module of the OWC breakwater. In the back, we have the slotted barrier. Here's the OWC hollow chamber, which allows the air trapped inside the chamber to be pushed up and down due to the incoming wave. And that up and down wave motion can power a bidirectional impulse turbine. This is the output voltage of the generator, and then this is the pressure differential inside the chamber. Typical traditional breakwaters are a rubble mound or pile type, where they have to locally source lots of rocks, stack them in, install them. It doesn't allow for the water quality to be exchanged, and it can't be removed. So this design is improving the function of a breakwater, integrating the slotted barrier to allow the water quality to flow through while reducing the amount of wave energy hitting the shore by extracting part of the wave energy to power the harbor.
As an electrical engineer, it's very interesting to me to try to merge, traditional power generation with turbines and things like that and put them in these more difficult environments. The ocean is a very unforgiving place and it's a difficult problem to solve, and I find it really rewarding when you do solve some of those problems.
We would like to thank the Navy for encouraging us to carry out more research on the flap system, because here is a good synergy between a DOE-supported project where we all began doing the flaps, and now we are bringing our knowledge to a different system.
I mean, having the opportunity to, to put the things in the water and to really test them and then go back and fix those and build on top of that, it's really how we can progress, in a meaningful way.
When I look ahead at the future, I certainly am hopeful as an advocate of wave energy in particular, but marine energy more broadly, that it continues and it grows. It can serve to fill in the gaps that wind and solar might have. If the sun's not shining and the wind's not blowing, there's a reasonable chance the waves are still churning away. Federal funding will continue to be crucial for the advancement of marine energy toward our aspirations. There's a lot of energy out in that ocean, and if we are going to capture it in a cost-effective, efficient way, we've got a ways to go, and so we need to continue to invest in this area.